Hi guys, welcome back to my channel, and today I'm going to be showing you how a segment tree works, how it was derived, and the code is very nice and clean, and the ideas behind it, if you understand how all of the bit stuff work, it's very nice and elegant. Okay, so what is the problem the Fenwick tree is trying to solve? Something called a range query with point update. So basically, what we want to have is we want to be able to take some array and compile some type of range query. And the special thing about a Fenwick tree is that it allows this even with updates. So if I have a couple elements and I try to query them, it'll also allow me to change one of the elements and everything will still be correct. So I can change an element, and in login time, the entire tree will be fixed up, and then I can start querying again, which makes it very useful for a lot of competitive programming and use scope problems. Okay, so let's see how it works. So this is an example for a sum query, and here we have the example array. At the bottom, you can see a good diagram of how the Fenwick tree works. So 8 represents the entire Fenwick tree. 7 represents just here. So how do we determine what's the methodology behind all this madness? How do we know, okay, 4 represents the last 4 and 6 somehow represents the last 2? So the way this is calculated is it is the least significant bit. That is the length of the range that this is responsible for. So basically how it works is, so the premise behind it is that if we query from tree K, if we query from tree K, that should represent the sum from K minus P of K. Let's say P of K is what I was talking about earlier, which is the least significant bit, plus 1 all the way to K. So let me show you what I mean in this diagram here. The representation of 8, the bit representation of 8 is 100. So the least significant bit is this, which is just 8. So this means that from 8 all the way back 8 positions, that is what this index of the tree is responsible for. One note, it's called a tree because of the way the ideology is formed, right? You have the parent to the different ranges, which would be the children. But this is actually implemented using an array, and it's very efficient because of these bit manipulations. Okay, let's look at 7. The bit representation for 7. Oh, sorry, it's 1000. The bit representation for 7 is 111. So the least significant digit is 1. So this means all the odd numbers would just be 1 long. Now for 6, similarly, it'd be 110. So we can see that it's 2. Okay? So why are we doing this? Why can we leverage this? Well, we're, we want this because of how we want this because of how we can leverage this to update and sum up the different lengths. So let's say I want to take the sum. Let's say that I want to take the sum from 7 all the way to 1. Okay? Then 7, as we can see here, is responsible for just the range 7 to 7 because of because P for 7 is just 1. So now, how do we include the rest of it? Well, what we do is we basically just knock this last bit, this p bit off. So for 7, p of k, p of 7 in this case, is equal to 1. So now when we subtract this from 7, we get 6. Now what is p of 6? That's 2. So if we subtract that, then it goes to 4. And what is p of 4? Well, that's simply 4. So then we finish the traversal. So let's see how it looks like in this example array. First, we take care of this range. Then we take care of this range. And then we take care of this range. So you can see every single time the size is doubling. And because we're doing subtraction, we're always moving back. So we're moving back here, using this, moving back here, and using this until it finishes. So as you can see, this is a very, very clean way. And because it's going times 2 times 2, it's log of n for any sum query. So now that we have this, how are we going to do point updates, which is the real magic behind a Fenwick tree? Because if I just wanted to do a sum query on a range, I would just make a prefix sum, right? So the magic behind this is in the same way that we can do a sort of bubble up for a range query, we can also do a bubble up for when we're updating a point. So let's take 3, for example, because that one has a lot of ways to bubble up. So first we look at 3, and let's say we change this to 0, simple case. So it goes to -4 for the sum query. So now this range is now made into 0 because there's nothing there anymore. And now we have to bubble it up. So how do I do that? Well, the way I can do this now is, remember, p of 3 is 1 because it's an odd number. So the way we do this is this time we add to it. So now it becomes 4. Now, why does this work? This works because of the way the bits are, this bit works, it will bring up the next biggest range that is affected. So as you can see here, the next biggest range is the one over here, and we'll just subtract 4 from there and make it into 12. Now, we don't want to do any of these that are strictly less than a, because that's not what it's affecting. But here, this is the next biggest one that's affecting. And similarly for 4, now we have to bubble this up to the full array. And this also works perfectly. What is p of 4? Well, that's just 4. So now we've bubbled it to 8. Because the length of the range that 4 is responsible for is 4. And the range with the next biggest size that encompasses it is 8. So then we look at this, and we'll also have to make this less by 4 and making it 25. So using the power of bits, we can do a point update in log n and a sum query in log n, which is extremely fast and very useful in a lot of cases. So let's look at the implementation. It's a lot simpler than you might think. Let's first go over sum. This section here, k minus equal, or k and negative k, is simply a way to do this p operation we talked about earlier. It's essentially just a way of doing this using bitwise operators, and it's more compact. So you're just saying k and negative k, and basically just finds the value we're looking for. And as I told you guys earlier, we subtract this to get to the next one. And whenever k is less than 0, of course, less than 1, of course, there's no more range to be added, and we just return the sum. So using a while loop and using this simplified version, you can see it's very simple, and this reflects exactly what the idea is. Now let's look at the add operation, which is even more simple because we're not storing a variable for the sum. So as I said earlier, we're doing our current value k plus pk, which is done by this sequence over here. And at every step in the way, we just to the current range we're working with, we add the update. So this was this was talking about the Fenwick tree. I hope it makes sense. And this way, you'll be able to remember the Fenwick tree properly, be able to implement it yourself when needed. A funny story, one time in a mock contest, I forgot what Dijkstra was completely. I'm not sure how. And I was able to derive it in the contest, which helped me get a better score. So I hope you like it. If you liked it, please subscribe, and I'll see you later.